if there is Newton's law of motion, then there is also Newton's law of universal gravitation. Now let us proceed to Newton's law of universal gravitation. Learning objectives. By the end of this section, you will be able to explain what determines the strength of gravity, describe how Newton's universal law of gravitation extends our understanding of Kepler's law. Newton's law of universal gravitation. It is the straight line that defines the most natural state of motion, but the planets move in ellipses, not straight lines. Therefore, some force must be bending their paths. That force Newton proposed was gravity. Newton's law of motion showed that objects at rest will stay at rest, and those in motion will continue moving in a straight line unless acted upon by force. In that force was gravity, or the force that attracts planets towards the sun. Newton was the first one to suggest that gravity is universal and affects all objects in the universe. That's why Newton's law of gravity is called the law of universal gravitation, as he is the one or the first to suggest this law of gravitation. He further hypothesized that gravity is not limited to Earth, but there is a general force of attraction between all materials bodies. Universal gravitation means that the force that causes an apple to fall from a tree to the ground is the same force that causes the moon to keep moving around Earth. It also means that while Earth exerts a pull on you, you exert a pull on Earth. In fact, there is gravity between you and every mass around you, your desk, your pen, your book, and even the tiny molecules of gas are attracted to one another by the force of gravity. There are factors that influence the strength of gravity. These are the masses of the objects and the distance between them. When we say masses of the objects with greater mass have a stronger force of gravity between them. For example, because the Earth is so massive, it attracts you and your desk more strongly than you and your desk attract each other. That's why you and the desk remain in place on the floor rather than moving one toward one another. And the distance between them, objects that are closer together have a stronger force of gravity between them. For example, the moon is closer to Earth than it is to more massive sun. So, the force of gravity is greater between the moon and Earth than between the moon and the sun. That's why the moon circles around Earth rather than the sun. Newton's universal law of gravitation. Newton's law of universal gravitation states that the force of gravity affects everything with mass in the universe. Newton's law also states that the strength of gravity between any two objects depends on the masses of the objects and the distance between them. Kepler's law. They describe how planets move in elliptical orbits with the sun as a focus. A planet covers the same area of space in the same amount of time, no matter where it is in its orbit. And lastly, Kepler's law, a planet's orbital period is proportional to the size of its orbit, or its semi-major axis. Why did Newton add to our understanding of Kepler's law? So, what did Newton add to our understanding of Kepler's law? Kepler derived his law's planetary motion from the vast amounts of data collected by Tycho Brahe. Brahe's observations were accurate enough that he was able to derive not only the shape of the planets' orbits, but their speeds as well. Kepler believed that the force from the sun pushed the planets around in their orbits, but he was unable to identify the force. So that is why Isaac Newton discovered that force and stated it as the gravity or gravitational force. Nearly a century later, Newton's work on gravity revealed why the planets orbit the way they do. When applied to the planets and the Sun, Newton's law of universal gravitation accurately predicts the motion of the planets. Newton also concluded that the gravitational attraction between two bodies must be proportional to their masses. The more mass an object has, the stronger the pull of its gravitational force. The gravitational attraction between any two objects is therefore given by one of the most famous equations in all of science, and these are the formula. Where F gravity is the gravitational force between two objects. M1 and M2 are the masses of two objects, and R is their separation. G is a constant number known as the universal gravitational constant. And the equation itself symbolically summarizes Newton's universal law of gravitation. Orbits in solar system. Learning objectives. By the end of this section, you will be able to compare the orbital characteristics of the planets and the solar system, compare the orbital characteristic of asteroids and the comets in the solar system. Orbits in solar system. An orbit, once determined, allows the future positions of the objects to be calculated. 2 points in any orbit in our solar system had been given special names. These are the following. Orbit, the path of an object or under the influence of gravity through space, whether that object is a spacecraft, planet, star, or galaxy. Perihelion of its orbit, the place where the planet is closest to the sun, Helios in Greek, and moves the fastest. The aphelion is the place where it is farthest away and moves the most slowly. Perigee in the apogee for the moon or the satellite orbiting in Earth, G in Greek. According to Kepler's laws, Mercury must have the shortest orbital period, or 88 Earth days. Thus, it has the highest orbital speed, averaging 48 kilometers per second. At the opposite extreme, Neptune has a period of 165 years and an average orbital speed of just 5 kilometers per second. All the planets have orbits of rather low eccentricity. The most eccentric orbit is that of Mercury, about 0.21. The rest have eccentricities smaller than 0.1. It is fortunate that among the rest, Mars has an eccentricity greater than that of many of the other planets. Otherwise, the pre-telescope observations of Brahe would not have been sufficient for Kepler to deduce that its orbit had the shape of an ellipse rather than a circle. The planetary orbits are also confined close to a common plane, which is near the plane of Earth's orbit called the ecliptic. The strange orbit of the dwarf planet Pluto is inclined about 17 degrees to the ecliptic, and that of the dwarf planet Eris, orbiting even farther away from the Sun than Pluto by 44 degrees, but all the major planets lie within 10 degrees of the common plane of the solar system. So these are the table of the orbit of the planets. The Mercury, which average distance from the Sun is about 58 million kilometer. Period of revolution, 88 days. Period of rotation, 59 days. The Venus, the Earth, Mars, Jupiter, Saturn, Uranus, and then Neptune. So these are the average distance from the Sun and period of revolution, as well as the period of rotation. Rotation, when we say rotation, this refers to an object's spinning motion about its own axis. The revolution refers to the object orbital motion around another object. In addition to the 8 planets, There are many smaller objects in the solar system. Some of these are moons, the natural satellites, that orbit all the planets except the Mercury and Venus. There are two classes of smaller objects in heliocentric orbits, the asteroids and the comets. But both asteroids and comets are believed to be small chunks of material left over from the formation process of the solar system. So the comets orbit the sun just like planets and asteroids do, except a comet usually has a very elongated orbit. As the comet gets closer to the sun, some of the ice starts to melt and boil off, along with particles of dust. These particles and gases make a cloud around the nucleus called a coma. The coma is lit by the sun. The sunlight also pushes this material into the beautiful brightly lit tail of the comet. The asteroids, these are the rocky fragments, are the leftover, the beginning of our solar system. Comets generally have orbits of larger size and the greater eccentricity than those of the asteroids. Typically, the eccentricity of the orbits is 0.8 or higher, according to Kepler's second law. Therefore, they spend most of the air time far from the sun, moving very slowly. As they approach perihelion, the comets speed up and wipe through the inner parts of their orbits more rapidly. So these are the figure of comets and asteroids. So today, Newton's work enables us to calculate and predict the orbits of the planets with marvelous precisions. We know 8 planets, beginning with Mercury closest to the Sun and extending outward to Neptune. Ceres is the largest of the asteroids, now considered as the dwarf planet. Okay, now let us sum up the Newton's universal law of gravitation and the orbits in the solar system. First, Newton's universal law of gravitation. Gravity is the attractive force between all masses. Is what keeps the planets in orbit. Newton's universal law of gravitation relates to gravitation force to mass and distance. It is the force of gravity that gives us our sense of weight, unlike mass, which is constant. Weight can vary depending on the force of gravity or the acceleration you feel. When Kepler's law are re-examined in the light of Newton's gravitational law, it becomes clear that the masses of both objects are important for the third law. Mutual gravitational effects permit us to calculate the masses of astronomical objects from comets to galaxies. It is also implies in Newton's laws that the gravity never becomes zero. It quickly gets weaker with distance, but it continues to act to some degree no matter how far away you get. Next is the orbits in the solar system. The closest point in a satellite orbit around Earth is its perigee, and the farthest point is its apogee, or corresponding to perihelion and aphelion for an orbit around the Sun. The planets follow orbits around the Sun that are nearly circular in the same plane. Most asteroids are found between Mars and Jupiter in the asteroid belt, whereas comets generally follow orbits of high eccentricity.